What up? It's time for Redman Codating. Today's gonna be pretty straightforward.
For part one, I highlighted some key things we should pay attention to. So they tell us that we discover a reindeer wearing a hard hat, and the reindeer brings us a blank topographic map of the surrounding area, which is our puzzle input. And so the topographic map indicates the height at each position using a scale from 0 to 9. And so for example, right here in the top left corner, this would represent a low height, and at this bottom left corner, this would represent a high height. And so they give us the definition of something called a hiking trail, which is any path that starts at height 0 and ends at height 9 and always increases by a height of exactly 1 at each step. And they tell us that you can only ever step up, down, left, or right, so no diagonals. They also give us the definition of something called a trailhead, which is any position that starts one or more hiking trails. And a trailhead score is the number of 9 height positions reachable from that trailhead via a hiking trail. And so we should pay attention to this score definition pretty carefully because the number of 9 height positions is different from the number of unique hiking trails, right? So for example, here we have one trail that starts here and ends here, and we have one trail that starts here and ends here. But what's important is actually that there's 2 separate 9s that we could reach. If there were 2 different trails, say one going like this and one going like this, and they both ended at the same 9, then the trailhead score would not change because we only care about the number of 9 height positions reachable from that trailhead versus the unique number of paths. And so the question for part 1 was, what is the sum of the scores of all trailheads on our topographic map? Let's get our input. You can see here I have the input next to my script. Parsing this input will be pretty straightforward. We'll simply open up our file, and for each row of numbers, we'll cast it into integers and make sure to save it all in one big list, or I'm going to use a tuple. So I'm going to say my grid is equal to tuple of map of int. So I'll make sure to cast each of my numbers to an int for each line, which has had the new line removed from the end for each line in my file. And if we print grid, we see that we get several rows of numbers as we would expect. So how can we approach this problem? One thing we might notice is that hiking trails can share a piece, right? So here, these 2 hiking trails share the first 4 numbers. And so one thing we might do is we might keep track of where we are as we go down the trail and see how many unique 9s we can reach from that point. And that way we'll repeat ourselves a bit less. We also know that each hiking trail will only be up to size 9. And so we can just try brute forcing, going in every direction and seeing if it forms a hiking trail and keep track of the unique end points because it won't be very expensive. I think at the worst it'll be like 4 to the 9 recursive calls, which is not that big. It's 200,000 calls. For a computer, that's pretty small. So let's implement it. I'm going to define part 1. It's going to take in my grid. I'm going to get the dimensions of my grid using length. And then I'm going to define a recursive function that allows me to step through different positions in my grid, keeping track of which number I'm at. And it will return all of the unique 9 ending positions that I've encountered. So I'm going to call this backtrack, and it's going to take in my I position, my J position, and it's also going to keep track of what number I'm at. So we always start at 0. And if our I is not in the correct bounds, or our J is not in the correct bounds, or the number at I and J isn't the current number, then we should return an empty set because it's an invalid part of our hiking trail. So we should say if not 0 less than or equal to I less than M, or not 0 less than equal to J less than M, or grid I J does not equal num, then I'm going to return an empty set. I use a set so that way we always only keep track of unique ending positions and we don't overcount. So otherwise, besides the case where you have a state that's invalid. What's our base case? Our base case is when we encounter the end of a hiking trail. So when we encounter a 9. So if grid ij equals 9, then we should return our current position, ij. So otherwise, what I want to do is I want to keep track of all of the unique ending positions that I can reach by stepping in one of the other 4 directions from where I currently am. So I'll keep track of that with a set. And then to step into different 4 directions, I'll just write out each of the directions explicitly, right? So I can either step right, I can step up, I can step left, or I can step down. And so I'll make sure to update all the unique end positions that I can reach, and I'll call my recursive function, and I'll make sure to update it with the step, and I'll increment my number by 1. And then I'll return all of the unique positions I've visited at the end. Then to answer the actual question of the sum of the scores of all the trailheads, I can just sum up all of the scores for each point in my grid. And to get the score, all I need to do is get all of the unique endpoints that I can reach from that position in the grid, and then take the length of that set. So I'm going to return the sum of the length of backtrack ij for I in range M for j in range N. And we get 841, which was the answer for part 1. For part 2, they give us a new definition. They tell us that a trailhead's rating is the number of distinct hiking trails which begin at that trailhead. And so if we look at this example, we see that there's only 1 start and 1 end, but there are 3 separate hiking trails we could take. And therefore the rating is 3. And they ask us a similar question. They say, what is the sum of the ratings of all the trailheads? And so this one probably fits our intuition a bit better. Now, instead of having to keep track of all these sets, we can just return 1 whenever we see an end, and then add up all of the ends we can get to from our current position. So we'll actually have to edit our code pretty minimally. I'll make a part 2. And the main change I'll make is that I'll replace all this set management with simple integers, right? So if I'm at an invalid state, then there aren't any ends that I can reach, and I'll return 0. And if I'm at an end, then I'll return 1 to represent that I've encountered 1 trail end. Otherwise, instead of keeping track of a set of end states, I'll just keep track of the number of end states. And instead of updating, I'll add. And here at the end, instead of summing the lengths, I'll just sum the return values themselves. And we see we get 1875, which was exactly the answer for part 2. One more note is that you might notice that all of these functions are actually pure, and that they exhibit something called optimal substructure, and you might think that we can benefit from caching our results. But because the trails are pretty small in the first place, the difference is pretty minimal. So this is a bit of a lesson in understanding our constraints before we jump to an optimized solution. In this case, using cache is pretty easy, but if we decided to cache it manually, we'd actually be wasting quite a bit of time when implementing. Thanks for watching. I hope this was pretty informative. I'll make sure to post these solutions on GitHub and put the link in my description. I also have the link in my description to my Discord server where I post LeetCode solutions daily and talk about algorithms on there. Let me know if you enjoyed this format and other videos you might want to see. Make sure to like and subscribe if you want to see more videos like this one. And yeah, have a good one.